Hello, hello. This is Postgres FM episode 76. My name is Nikolay, and as usual, together with me is Michael. Hi, Michael.
Hello, Nikolay.
So today's topic is super interesting and very popular, right?
Not exactly. I chose this one.
Okay.
Therefore, it's boring.
But we will learn something new, which is good.
I hope so.
Even if it's useless, it's still new. Good. We're here to learn, right?
So Nikolay's teasing me because I've picked the topic hash indexes, which are, until relatively recently, were highly discouraged by the Postgres docs and not very sensible to use. But
until Postgres 10.
Yes, but have been in Postgres for a long, long time. I looked into the history of it. And therefore, some people must think they're useful. And I definitely think there's one or two use cases for them. But more to the point, I think they're very interesting for people. I think this is the kind of thing that will make you appreciate the btree index as well. And also understand a little bit more about trade-offs we make when we're choosing things within Postgres.
Indexes, right? I mean,
yeah.
Why doesn't Postgres choose index type for us? We just want make it fast and that's it, right? It should choose. Okay, different question. Are hash indexes more useful than the money type, data type?
Oh, I think so, yes.
Okay, this is already better. I hope we will never have an episode about the money data type.
Yeah, right? Me too.
Okay.
So yeah, should we start with what a hash index is?
Yeah, hash function, hash index, right?
Yeah, that's pretty much it.
Hash table.
Yeah. So in fact, that's a good point. A lot of people have come across hashing from looking at query plans for hash joins, or backend engineers very familiar with hash tables. Can be a very efficient way of taking a value, hashing it. In this case, we get Postgres behind the scenes is calculating a 4-byte integer, storing that, and then in future, if we want to look up the value by equality and equality only, we can hash the value we see and look it up in the index in this case. So people that like theory talk a lot about big O notation, don't they? So this is one of those things that I struggle to love, but it has a low, O1 is what people often say. I'm not sure it's strictly true, depending on how deep down that rabbit hole you dive. But yeah, it can be very, very efficient for looking up things by equality, especially in certain conditions. So that's you actually, a couple of things on details. I didn't realize you could, and it makes sense, but you can use a hash index on any value, any data type, which is quite cool. I guess the same is true.
Postgres has a lot of internal hashing functions for all data types and also for the record. So you can say record for some table, and it will give you a hash, integer 4, right? Regular integer, 32 bytes, bits.
32-bit, 4-byte, yeah.
Yeah. And I actually recently rediscovered it and used. It was interesting. I didn't use the hash index, but I used one of probably hash text function. It was hash text function. I needed to, when you need to reindex a lot of indexes, and it's a huge database. For example, after upgrade to Postgres 13 or 14 especially, you need to reindex a lot of btree indexes to start benefiting from the optimizations Peter Gagan and others implemented. And obviously, you need to reindex. Okay, you will do reindex concurrently and so on. It's good, but question will be how to move faster. There are parallel workers, as we discussed, and so on. But probably you will decide to use multiple processes to issuing the reindex concurrently command. And in this case, if two of them try to reindex two different indexes which belong to the same table, you will have a deadlock, right? So my obvious idea was we just need to attach each table associated with particular worker. And to do it, I just took a table name, calculated hash text from it, and then modulo number of workers. If I have, like, for example, 5 workers, so we have table name, hash text function. The hash text function produces number, like integer 4 number, and then we just modulo 5, like remainder of the division. It will be like 0, 1, 2, 3, 4. That's it again, and 0, 1, 3, 4. And each index associated with particular table name will always go to particular worker. So there will never be a conflict, no more deadlocks. Right.
Nice.
So this is how you can redistribute work. So maybe also check if you need to redistribute. You need to check a lot of indexes for corruption. You can also use many, like 16 workers, for example, and you redistribute work like to avoid deadlocks. So hash text is useful. I was already like CRC 32 or something. I was thinking, I need to. Oh, by the way, I asked my bot to advise me. And it says, there is hash text. Hash text. I never used it before, or maybe I just forgot. And then if you in PSQL, if you say \df, then hash star, you will see more than 50 functions. We checked it before the call. More than 50 functions. Many of them return integer 4. Some of them return integer 8. So it's good to have a lot of already implemented functions. You don't need to care, just use it. Right? Good?
Yeah,
yes.
Absolutely.
Small comment, slightly off topic.
Yeah, I mean, related to hashing, but I guess completely unrelated to hash indexing. Yeah, exactly. Yeah, so you mentioned already there's a big change in the history of hash indexes that I think is worth mentioning, and that's the version 10 made hash indexes crash safe or write-ahead log.
Right, hold on. Mm-hmm.
Which is really important. Like before that, it meant if you had it made them basically unusable or unsafe to use, especially in a high availability setup. If you had replication and then failed over, your replica wouldn't have that index. And if you're
ephemeral indexes,
right.
But no more. So it's solved. The same was solved with Gist very long ago. Originally, Gist was also not wall supported in wall at all, but it was like 20 something years ago it was implemented.
Well, speaking of 20 something years ago, I was trying to find out when hash indexes were added, and the Git history doesn't go far enough back, I don't think. And the docs, the online docs 7.2 is the oldest version on the online docs, and they have hash indexes. So that's as far back as 2002 already. So they're more than 20 years old as well.
Well, I'm quite sure they are older because it's maybe one of the simplest type of index you can implement. But interesting that wall was not implemented so long, right?
Right.
Until 2017, right?
I think you'd struggle to get. I could be wrong, but I think if we didn't have hash indexes in Postgres today, they wouldn't get added, and they would be encouraged to be added via an extension. That's my guess as to how they would be implemented if they were done today. But I mean, I might be, or maybe via the contrib modules.
Well, yeah,
maybe. But we have them. They're first class supported. They're well logged now. They're replicated and everything. Crash safe, even while they're doing complex operations. We might get to a bit later. It will recover, so we can use them if we want to. I guess the question then is, why would we? And you mentioned something before the call I found very interesting, and it's probably very telling. But should I ask you, have you ever used a hash index?
Only in experimental environments, never on production. I think I saw them in the wild, saw them, and was super curious.
I can believe that.
Yeah, but I don't think I ever seriously considered them. But you need to take into account that version 10 and later it's already my mostly consulting practice. Before that, I created a lot of systems, social networks and so on. There, it was before Postgres 10, so never considered them. So my memory says stay away from them.
Yeah, that's a really good point. So it's only since 2017 that you should even be considering using these. So I'd like to first cover, I know there's going to be quite a few limitations that we need to talk about, but I'd like to cover some of the potential benefits of hash indexes. I think there's a couple that are worth mentioning.
The size?
Yes. So they can be. So imagine if you are hashing a fairly large string or even number, or just a piece of data that is more than 4 bytes. When you are indexing it with a hash index, it's only having to store 4 bytes, or a bit more, but it's not having to store that value in the index. And that means for larger data types or larger values, it can be significantly smaller than a btree index with some caveats. Naturally, there are some optimizations for btree that we've got in recent versions, and it really stands out for larger values basically, and for indexes that are unique or mostly unique, for columns that are unique or mostly unique. So that's a big difference as well. But there are cases like that, right? I did a collaboration with Haki Benita for his blog, and he did a lot of the work. He deserves most of the credit, but he put me down as a co-author, which was kind of him. And we looked at quite a few things, and for the use case that he had for hash indexes, which was a URL shortening service, you get some quite large URLs can be quite large strings in the grand scheme of things, especially full URLs. So they actually came out quite a lot smaller when you put a hash index on it versus a btree, which is pretty cool, even post deduplication, because these are largely going to be unique. We didn't make them completely unique, but largely your URL shortening thing is going to be unique strings. So yeah, they can be significantly smaller. They can be significantly bigger depending on your data. But I think size is underrated in terms of index types. I think not only we're going to look at performance in a bit, but space in the cache, we've talked about this kind of thing before, but I think it is worth mentioning.
Yeah, by the way, if we try to index in a regular way with btree some large text values, there's some limitation. I always forget it.
Good point.
Yeah, so sometimes we just need to apply hash and use expression btree on top of it. But it's not, of course, it's not hash index, but we use combination, right? In this case, we cannot order these values, but for exact matching, this is what can work well. Right?
Why do you hash it and then put a btree index on instead of just putting a hash index on?
Because again, I'm old guy. Again, my memory stays away from. By the way, with my bot and GitHub, we just checked when hash build, the hash build function was added, and it's 27 years ago. Original Postgres 95.
27.
Yeah, original source code of Postgres 95.
Wow.
Committed by Mark Fournier. It had already this hash build, which builds a new hash index. So this is super old stuff. I think maybe it's even came from original Postgres. Obviously, it came from original Postgres. Maybe even from Ingress. Who knows? So maybe it's even more than 30 years ago.
Yeah, very cool. But yeah, that's another advantage, right? There's no limit to the size.
So you think, that's great. So you think I just can create hash index if I have very large text values?
You're losing the same things, right? You can't order by them. And you're kind of doing a self-rolled one, which maybe even proves that we don't need them. But I think less footprint, right? Because you're having to, I'm not sure. I think there might be some weird trade-offs around maintenance, but I think you'd largely recreate them, yeah.
So if I say create table T something as select, and I say repeat as column C1, and I repeat some letter a million times, I have obviously text value million letters. Then I say create index on this value, on this table, on this column. In this case, btree will say index row requires 11,464 bytes, so 11K, right?
Mm-hmm.
In my case, but maximum size is 8K. Okay, like block size. But if I say using hash, right? Using hash, same column, create index. Yeah, it works. So why do I? Okay, I'm old guy. I have old habit. I need to get rid of it. Actually, this is perfect case.
Consider it.
Large text values. I don't need to hash first and then btree. I just hash index in this case. I will need to think about it. Thank you. This is
There
unexpected.
are some reasons you
actually.
might not
Simple.
want to do this.
Why?
Okay, well, let's go through the positives first. I promised
Let's do it.
positives. Size can be worse, but it can be a lot better. Speed can be better, not just lookups, but also average latency of inserts. I definitely had some discussions with Hacky when we were reporting these numbers that we could have done a better job, I think. I hold my hands up. This was a couple of years ago, and I've learned a lot since then. But insert performance on a batch was, or when we were inserting one row at a time, was about 10% slower, I think, for the btrees than versus hash, which I was a bit surprised by because I knew there was some overhead around splits for hash indexes, or higher overhead some of the time. But lookup performance.
But B3 also has split sometimes, right? So
yeah,
obviously. So we need to compare.
Yeah,
in this case, we cannot say hash index has this disadvantage and that's it, right? B3 also has this disadvantage.
Yeah.
Yeah.
So they're kind of bigger splits less often. Yeah, that's a good point. But lookup speed, I was expecting a difference, and admittedly, they're both really fast, right? We're talking about basically key lookups. So btrees, we've always raved about how good they are at like key lookups, right? That's what.
Yeah, just few pages to find proper reference to like if it's just a few blocks to fetch from disk or to read from page cache, and then.
And I think we did about 100,000 lookups, and it was both of them were under a second to do 100,000 lookups.
So you haven't checked buffers at that time, only timing, which is quite volatile.
Again, I would do some things differently now. This is a couple of years ago, but the lookups, whilst they were both under a second, I think it was something like 30 or 40% faster for the hash lookups, which was, I thought, actually quite significant. So I think there are some cases where, in some extreme, if you've got long strings and you only care about uniqueness lookups, then I think there's a case for using them. But that is obviously a very narrow, very specific use case.
Wonder in these tests if you considered the planning time, because I guess if table is not absolutely huge, like billions of rows, in this case, planning time can be maybe even a bigger contributor than index scan itself, right? So we need to exclude it using like maybe prepare statements and consider only execution, right?
That would be a good test, but also why would the planning time differ between index types?
I'm not saying it differs. I'm saying if you're comparing with like latencies.
Yeah, sure. True.
What percentage of planning time is there and here? So we need to exclude it to compare clean numbers, right?
Yeah, that'd be great. I don't think we used prepared statements. I'm pretty sure we didn't.
And honestly, I wouldn't look at timing here at the first. Like as first metric, I would still prefer looking at buffers. But okay.
But the point is they can be more efficient, and that's partly because if you imagine a B-tree structure, you might have to go through a few through a few hops, especially once your table gets really large. Now we've talked about partitioning so many times, right? So you could argue that you could keep your B-trees relatively small in the grand scheme of things, but if we do get large enough, the hash structure is just so much more efficient, and that will show up in buffers as well, right? So that is the argument, I think. So you've got potentially smaller indexes for certain, for highly unique, slightly larger data types, and potential benefits on the insert and lookup speeds.
Have you considered collisions? Because if you have only integer 4, obviously you might have collisions, and you need to resolve this additional hops, right? Additional comparison and so on. Have you considered this? I guess trying to measure some edge cases. Maybe?
I looked into this. I looked into the internals a bit. Well, actually, there's a couple of really good internals pages on the Postgres docs on hash indexes. And there's only a throwaway word quite early on in one of them that mentions that they are a lossy index type. So it's not the only lossy index type, but it means that just because we get a match for the hash, the 32-bit integer, doesn't mean we do actually have a hit. We could have a collision. So there is a recheck, and you can get rows removed by index recheck type things in your explain, but I haven't seen it. Like we're talking, you'd have to have. Well, I'm not so sure you'd have to have billions, but I'm guessing you'd start. In the tests I've done, I haven't seen any. But I guess you'd pay that overhead for every lookup, right? Like you're having to do that recheck all the time because they're lossy. It's not just when there are collisions that you pay that recheck. So those numbers I was talking about include the overhead of rechecks.
Okay. So what are the downsides? Why shouldn't I use
so many?
So many. Okay, index only scan, as I remember, right?
Yep.
Lack of index only
because
scan.
we don't have the value in the index. It's literally impossible to have an index only scan.
Right. And that's bad.
Yeah.
Yeah. So, but if in my case, if I have large text value, and I consider hash index versus btree over hash expression.
You can't have an index only scan there either.
Yeah, because I cannot fetch the original value. So it's not a reason that would stop me from using hash index. Okay.
No.
Right.
In fact, have you considered collisions for that?
Yeah. Well, yeah.
You had to implement it yourself.
That's true, yeah.
So I think the big one is ordering. Obviously not in the case you're talking about where you're hashing, but the big advantage btrees have is they order your data, and that it supports so many different things.
And greater than, less than comparison, obviously. So it's
range scans. Yeah, it feels like a limitless number of things that then enables.
Right, you can deal with collation issues. It's so cool. They can be corrupted because of collation change.
I mean, that's a good point.
So
maybe hash indexes are less likely to get corrupted.
Right. Okay. It was
actually. What if the hash function create a different value instead?
I don't think it. Yeah, it's a good question. I don't know how it's implemented internally. It should not be super difficult, but obviously, how will it hash non-latent characters and so on? And does it depend on glibc version change, for example? It's an interesting question. I never had this question because, again, I'm not seeing them in the wild often at all. So.
Another huge difference, and I don't think this is necessary based on its. I don't think this is like the index only scans where it's literally impossible. But in Postgres we can't use hash indexes to enforce uniqueness. So for unique constraints, which is a big deal. Like that's a really for example, we can't use them for primary keys, or there's no point because we've already got a btree index on them.
Okay, good to know. What else? Multi-column, right? I remember now. Multi-column.
Exactly. So we don't. So hash indexes don't support multi-column.
You can combine values, or you can I don't know. So yeah.
But more to the point, one of the big nice things about multi-column btree indexes is we've also got the sorting, sorted by the first column, then sorted by the second. So we just don't have advantages like that, and it ties into the index-only scans as well, right? One of the best things about multi-column indexes is we then get potential for index-only scans as well. So these things, a lot of them interplay. One difference that isn't necessarily an issue, but I found interesting, I thought you might as well, was that the fill factor for hash indexes is 75 by default, whereas btrees is 90. Really interesting.
Some old decision, I guess. Maybe no, but maybe, I don't know. Yeah.
My guess, in the blog post, we looked at what does it look like if you change the fill factor to 25, 50, or 100, and at 100 versus 75, you see it not getting larger as quickly, but when it does, it bounces at a faster rate. So as the index grows, it grows less at first and then more all at once. So my guess is it's some trade-off between general size and performance and the impact of splits, or the cost we pay at splits. And in fact, this is probably the biggest one you'd want to consider on the difference between doing a btree index on a hash function versus using a hash index. And that's how insert performance would look in terms of probably not average latency, but maybe the standard deviation of latency. So with hash indexes, the way they're structured, we have buckets that values can go into. But beyond a certain size, Postgres works out, and it handles all this for you. It decides, oh, we need more space. It'd be best to have another bucket. Let's split one of the existing buckets. And then we pay that overhead during the insert, right? Like that, it can slow down your insert. So my guess is the standard deviation for inserts would be perhaps significantly higher than btrees, but I haven't checked. It's one other thing I would like to do.
Maybe.
But so on high throughput, it's also, there's a note in the internals document about high throughput. Let's say you've got a really high throughput table. You might actually be better off with your btree index that you mentioned than a hash one.
Okay. And multi-column index, I think we can... I've just checked, by the way, hash record applied to whole table row. It works. Produces integer for number. It works. I think we might probably decide to use it to... I remember I was always using the MD5 hash, converting row first to text and then MD5. But maybe hash record is a better choice when we need to, for example, compare the content of two snapshots row by row, like to find which rows were changed, comparing them, like joining by ID, by primary key, for example, and then we compare hashes of whole row, right? In this case, hash record is working. I wonder if multi-column index is not supported. What if we just combine multiple columns and produce hash out of them, and almost the same, right? It's strange that it's not supported. Actually.
I mean, we can still only use uniqueness lookups, right? So
yeah,
I guess it's the case where you want to see if two columns, when combined, are equal to the record you've stored. Yeah, but I'm not seeing the same benefits.
Okay, I will check a couple of things more.
Yeah.
Any more limitations, or that's it?
Don't think so. I might have missed one, but like those for me are they're substantial limitations. And I think if you're like when you're designing a system or you're choosing an index type for a new feature building, and it turns out that right now the hash might just about come out on top. Maybe you get a slightly smaller index, maybe your lookups are slightly faster. I'm not sure I'd still advise using a hash index. I think I might say, look, if your requirements change in the future, if you ever do need to look up like a range of these values, if there's some analytics you might need to do on it or something, you might have been better off with a btree index. You've got that extra flexibility. You've also got, I think, probably more effort being put into optimizations on them going forwards. If it's a tight call between them, I might still encourage people not to use them in general.
I never did it. I just did it. I used hash record function applied to whole row in a table, which has 3 columns. And then I created index on top of that hash record. So first time I created an index not specifying columns, but involving all columns in a table. This is super strange. It could be btree actually as well, because hash record produces integer 4, right? So it applies to all columns. So I said create index on T1 using hash record of T1. That whole record. That's super strange. I need to think.
What use case are you imagining for this?
I don't know. I'm just exploring. Curious. I don't know. Maybe to track which records changed content or something. I don't know. It's just interesting that it works. I thought we are required to specify columns, right? When we this column, that column, but here you just specify whole record, and it works. This shows flexibility of Postgres as usual, right? Yeah, but I created multi-column index hash, but it's hash of hash, so it's double hashing here. Okay, so I don't know. I'm still thinking about use cases. I still only realistic one is only these really large text values. That's it so far for me.
Yeah, and when you only need unique lookups of them.
Mm-hmm. Yeah. So yeah, interesting. So I will keep it in mind. something
Yeah,
new.
I love that
Yeah.
we've gone that during this episode we've gone from I never
Something
have use cases
practical.
for hash indexes. Yeah, exactly. There we
Something
go.
practical. Cool.
But I also think, you said you've seen them in the wild. I think that might be a result of people overthinking it. And I was there a couple of years ago. I was thinking, there might be some cases where that difference is meaningful and worthwhile. But for the flexibility, I think, anyway, I've said that a few times now. Cool. Well, thank you, Nikolay. Thanks for indulging me. Hopefully a few people found that interesting and useful. And yeah, catch you next week.
Thank you. Bye bye.